Welcome to this lecture on differentiation of a quadratic form. We will differentiate a quadratic form by a scalar, then by a vector. We will also differentiate an asymmetric form. Let us differentiate Q equals x transpose Ax by x, where A is a matrix and x is a vector as given below. Notice that Q equals x transpose Ax is a scalar. Its derivative with respect to x is a vector. Let us start with Q equals x transpose Ax. Let us write down x transpose. It will be horizontal or a row vector times A times x. Let us multiply it out. I will retain the row vector as it is. I will multiply this matrix and this vector to arrive at this. First row into this vector, I have got this. Kth row and this vector, I got this, and so on. What terms will be non-zero when differentiated by xk? So let us start with the same expression. When differentiated by xk, non-zero terms will come from the following. Notice that in every row you have xk comes in only one term of these n terms, except in the kth row. So there will be a contribution from here because xk comes here, and there is an xk comes here because it is multiplied by this xk. So as a result, we write like this. Non-zero terms will come from there. These are the terms that have xk that corresponds to this, and this row gets multiplied by this xk, and hence I have that row as well. So now we can differentiate this with respect to xk. When I differentiate, notice that if I differentiate this of this row, I get everything inside the bracket, which is nothing but kth row of Ax. This is the matrix Ax. If you take the kth row, it is that. That's what comes here. That's what is here inside the bracket. And what about this? This is nothing but the kth row of the transpose. To see this, note that I have k1 here, I have 1k here. So we can say that this is nothing but the kth element of ATX. This is a scalar, because if you add all of this, you will get scalar, and this k goes from 1 through n. So let us start with this expression that we derived in the previous slide. We will define del x of q as this vector acting on this matrix q. The first element is del by del x1, partial with respect to x1, and so on. The final entry is partial with respect to xn. So this is the expression for the first row here. You come here and replace k with 1, you get this. Do the same thing for del by del x2, x3, and so on, all the way up to del by del xn. When I complete it, I get this matrix. Now notice that elements here form the vector Ax, whereas this forms the vector A transpose x. So I get this expression. If A is symmetric, then A will be equal to A transpose. As a result, it becomes 2Ax. So we arrive at the expression del x of q, which is a vector, is this. notice that q is a scalar. We are differentiating the scalar with respect to a vector. We will get a vector whose value is given by this. Now let us take an asymmetric form x transpose by by x. So let R be equal to x transpose by. Let us write it out, x transpose b times y, and let us expand this. What will this be? This row multiplied by this column, that is the summation, that will come in the first row, that will be multiplied by x1. So x1 into first row here after multiplication, which is this. Similarly x2 into second row and so on. Kth row, kth element here and kth row here, which is this, and finally the last element here and the last row here, which is this. So this is the expression for R. Now let us differentiate this R by vector x. So we will differentiate this with respect to x1. So I will get only the first entry here. And what is the first entry? It is nothing but the first row after multiplication, first row of by. So that is the partial with respect to x1. Then when I do a partial derivative with respect to x2, I get the second row and so on. Finally I arrive at the last row. So I get this matrix on differentiation, and this is equal to by, because you have all the rows of by. So this becomes by. What happens when you differentiate this with respect to y? All that you have to do is you take a transpose of this. Notice that this is a scalar because you have a vector here, row vector, here it is a column vector. When you multiply, you can see that it is an element or a matrix of size 1 by 1. In other words, this is a scalar. Because it is a scalar, I can take a transpose. So I differentiate this with respect to y transpose b transpose into x, and using this formula I get b transpose x. So I get this expression, okay, because this is a scalar. We derived the following: del x of q is given by ax plus a transpose x. It is equal to 2ax if symmetric. Then del x of xt by was shown to be by. We also saw del y of x transpose by to be b transpose x. To conclude, we derived derivative of quadratic forms. These are used in the derivation of linear quadratic regulator. With this, we have come to the end of this presentation. Thanks for joining. Goodbye.